Hey everyone, welcome back to another video. Today I wanted to go through everything that you need to know for stereochemistry in the GAMSAT. So when I think about stereochemistry questions in the GAMSAT, really I think there are three distinct kind of frameworks that I would put those questions into. I've given these kind of my own unique names, but what these are stereocenter questions, rotation questions, and configuration questions. So if you can understand all three of these frameworks, I think you'll be able to answer almost all, if not all, of the stereochemistry questions in the GAMSAT. And as always, if you find this video helpful, I'd love it if you could like, comment, and subscribe. All right, so the first thing that I'd like to go through are the stereocenter questions. Now, what a stereocenter is a carbon atom that is bonded to four different groups. So if you look down into the bottom right, you'll see that here we have a central carbon atom and we have four different groups attached to it. We have a hydrogen, an OH, bromine, and a chloride. Don't worry too much about these lines that look a little bit funny, like these two over here. At the moment, I'll explain what they mean later, but for now, all you need to know is that those lines and those triangles, etc., they just mean bonds between the carbon atom and all those things that are attached to it. Now, you may also see stereocenters referred to as chiral carbons. So these two are exactly the same thing, but if you see anything about chiral carbon or stereocenter, it means you need to find carbon atoms that are bonded to four different groups. Now, this big, scary looking molecule that I've put here is kind of an example of what you might see in a question. So it might say, which of these, how many stereocenters or how many chiral carbons does this molecule have? Now, I'll link back to my other video on organic chemistry, which kind of goes through how to draw compounds out, because if this doesn't make sense, then you really do need to look at that other video. But assuming that you know kind of how to interpret what this molecule is, we should be able to quite easily pick out the stereocenters. So I always kind of look for things that just obviously have four different groups attached to them. So we can rule out, or the other way around, look at groups that definitely don't have four different groups attached to them. So the examples that I'm thinking of that don't, I'll do them in red, is these things here. All of these carbons, they don't, because, how do I know that? Because they've got this double bond here. So if there's a double bond, that automatically tells us that that carbon is bonded to something twice. So that means it can't actually have, four distinct groups. So these ones are automatically ruled out. Now, if we look at, in comparison, something like this one here, that does have four distinct groups. So if we go, I like to kind of think of it as, can you, if possible, make a different group if you had to. So if you kind of go down this way and this way, they're the same. But if we keep going, then this part will be different. And we physically cannot make that same structure on that other side. So that means these two groups are different. And if we, it's going to get a little bit messy with the colors here for a second, but if we kind of look here, we can see that we can make that, but this one has an OH group here, whereas this one has an OH group here. So they are kind of distinct groups. So sometimes when you are making these stereocenters, you do need to go past just the first four things that it's bonded to. But I just kind of try to think of it as, is it possible to make a different group? Because it can get quite confusing when you get these ring compounds, but I just like to think of it that way. Is it possible or is it not possible to make a different thing? If you can make a different thing, then that's a stereocenter. So as we keep going through, we can kind of rule out a few more of these. So that one and that one. Why can I rule those ones out? Because they don't have any other groups attached to them. So that means that there's some hydrogens attached here. So I know that they're not stereocenters either. Same with that one. Whereas something like this one would be a stereocenter. And again, I would just track. So I'd go, okay, this way I've got that. I've got a hydrogen out here, which isn't listed, so I'll do that in yellow. If I go this way, I can make something, and I get the same if I go that way in brown. And then if I go this way, that's the same. That way, that's the same. But I've got, again, this OH group, which makes it different. So it's just kind of a bit of a, I don't think there's a quick way to do it. You just kind of need to look at those things and be able to identify the stereocentres. But that one in green definitely is as well. And then we can kind of rule out this one, this one, this one, and this one, again, because of those hydrogen. And if I look at that one, that looks like a stereocentre as well, because you can't make the same group if you go in different directions. So I hope that was kind of helpful in terms of how you can identify stereocentres. I think the best thing is to just bring up some molecules and then try this process out and pick them out, and then look at the answer and see which ones are stereocentres. And it may seem basic, but I promise you, if you look through the practice material, you will definitely find questions that are literally just saying, how many stereocentres does this molecule have? Okay, so the second framework I wanted to go through are what I call rotation questions. And what you'll essentially see is something along the lines of, are these two molecules the same, or are they stereoisomers? So to be a stereoisomer, you need to have a stereocenter. So you need to have two carbon molecules with 4 different groups attached to them. So if you look at each of these molecules, they each have 4 different groups attached. And there'll be something like, are these stereoisomers? Are these enantiomers? That's another term that you might see. Or are these the same molecules? So just have an idea of all these different words that they could use, but they all mean exactly the same thing. Now, when we actually need to go about determining if these are the same molecule, what we need to do is rotate them into the same plane. So what I mean by that is these dashed lines mean that that molecule they're bonded to the carbon atom, but they're pointing away from you. And these solid triangles mean that they're pointing towards you. So I'll get a little example in a second, and that should hopefully make a little bit more sense. Okay, so I'm on a bit of a budget and I don't have any of the proper kind of chemistry models. So this is the best we've got. I've sacrificed a mandarin and put a few pens through it. But what if you can think back to that molecule that I had? We had a carbon atom, which is the mandarin, and it's bonded to 4 different groups. So the tip of these pens are the different groups that are attached to it, okay? Now, I said that the dashed triangle, the dashed wedge, is pointing away from you, and the solid wedge or triangle is pointing towards you. So if I had it something like this, it's not perfect because I'm using a mandarin and some pens, but in this case, this one would be pointing towards you, and this one would be the one pointing away from you. So this would be the dashed wedge, that would be the solid wedge. Now, when we need to determine if these molecules are the same, they're kind of at all these different angles. So what we need to do is to put them in the same plane, and how we do that is rotate the molecule. Now, if you kind of keep your eye on this one, which is pointing towards you, and this one, which is pointing away from you, if I rotate the molecule, what happens to those two groups? Well, they're all kind of just spinning around. But this one at the top and this carbon atom, they're not moving. They are staying in the exact same plane, and everything is kind of rotating around it. Okay? But I could rotate it this way as well. And now the one at the top and the bottom, they're rotating around, but this one is staying the same. So when we rotate these molecules, how I like to think of it is I hold one of them still and I just twist them around that one that's staying still. So by doing that, I can move the position so that they're consistent with the other molecule, and then I can determine if they're the same or if they're stereoisomers. So I hope that made sense. I've got the thing here so we can kind of visualize it as well, but I thought it'd be good to show you on the big camera first. So if we look at, let's say the molecule on the left, this one here would be Z, and this one here pointing away from you would be Y, okay? So when I think about these rotation questions, I'll put the mandarin down for a second. We need to rotate these molecules so that there are some things in the same plane, because if two things are in the same plane, we can kind of compare them a little bit easier. So you can do literally any of these that you want, but as I kind of said with the Mandarin, you want to hold one of them still. So I'm holding this black one. You'll notice that the black one doesn't move and everything else rotates around it. All right, so this is a really important concept because you're going to need to do this a lot in stereochemistry. So for example, what we could do is I could hold this one at the top at W. Actually, sorry, that's not what I want to do. I could hold, let's say, this Y here. Okay, and I can now twist that Y. So I can imagine just twisting this Y. If I held that Y and I twisted the molecule, what would happen? Well, these three are going to rotate around. So the Y is going to stay in the same spot, but all of the rest will rotate them. So I'm going to do it exactly how these arrows have gone. So I'll redraw the molecule, what it would look like. So we'll get the X will go to the top because we've twisted it up. So you'll see that we've twisted it from here all the way up to the top. The W will go here. The Y will stay in the same position. And then this Z will jump over. So a mistake that I see a lot of people make is thinking that they can just rotate them around like this, but it doesn't work because of the planes that everything is in. So again, if we take this example, they're not all rotating because they're in different planes. So there's one that's going to be stationary. So I'm sorry that I'm repeating myself, but it's quite hard to get your head around, but it is really, really important. So I really want to hammer that home. So now that we've rotated, so I'll rub out all these things so we don't get confused. So I have rotated this molecule here. I'll do a different color. So I've rotated this molecule. So we don't really want to look at that anymore. We've rotated it into this molecule, okay? So these are exactly the same molecules. It's just been rotated. But now you'll see that we have the X at the top and we have this C. So we can start to kind of compare if they're the same molecule or not. Now, once you've got two things like this lined up in the same plane, you can then just take the order of the other remaining molecules. And you just need to be consistent when you're comparing them. So for example, I could start at this Z here and go clockwise, and I'll just write down that order. So my order as I go from the Z clockwise is Z, W, Y. All right. Now, if I take the same molecule, the second molecule, and I start at the Z again, and I go clockwise. So as long as I'm consistent, this will work. I also have Z, W, Y. So these two molecules that we started with are the same molecule. If this order was different, if it went Z, Y, W, then they are stereoisomers. And what that means is they have the same configuration, but you cannot rotate them. So I just thought, because that one got a little bit messy with all the colors, let's just start from scratch and just quickly go through an example just to apply what we learnt. So you'll see here that none of these are in the same exact position. So what we would do is want to move one of these things to the same position as the other molecule. So what something that looks easy to me is kind of getting this Z down here, down to the bottom. So what I might do, I might just hold this Y and twist them this way. Okay, so I'm holding the Y and just twisting them around. So this molecule would then become, that's a W, that's the Z, that's the X. So you see that now I've got, if I highlight that again, I've got the C and the Z in the exact same position. And now I would just I'll start at the W and I'll go clockwise again. So on this one, I get W, X, Y. And if I start here and I go clockwise, I get W, Y, X. So these two molecules are stereoisomers. So that's exactly how I would go through any kind of stereochemistry rotation question in the GAMSAT. Okay, and lastly, we've got configuration questions. So there's a fair bit of overlap between these configuration questions and the rotation questions. We're using a few of the same skills, but there's just a few extra things that we need to do. So the first step is that we need to prioritize. Now, how we prioritize is in order of descending molecular weight. So the thing that is the heaviest will have the highest priority. So you don't need to know every atom out there, but I'd definitely know your carbon, hydrogen, oxygen, chloride, bromide, those kinds of things, or chlorine and bromine, sorry. So definitely know where those kind of roughly are in the periodic table. And what we care about is the first atom that the carbon is bound to. So if we take this example of the CH3 up the top here, the first thing that it's bonded to is the carbon, because we know that carbon can form 4 bonds, but hydrogen can only bind one thing. So we can't have a hydrogen bonded to that carbon because then it's forming 2 bonds. So it must be the carbon bonded to the hydrogen. Okay, oops. So that's a little bit messy, but we know that the first thing, if we look at this group at the top, is the carbon. Same thing with the hydroxide, it must be bonded to the oxygen, and then we've got hydrogen, and in this group, you kind of need to know a little bit about those carboxylic acids. So again, that's in my organic chemistry groups video, so I'll link that video in the description. But that will be also bonded to the carbon atom. So, okay, well that's great. So we know that oxygen is the highest, so that's great because out of all those 4 groups, oxygen is higher than carbon. And we can also put in that hydrogen is 4, which it usually is. But what about those two, because we're bonded to carbon in each of the methyl and the carboxylic acid groups. So that's why I made a bit of a point of it to really be clear on what's bound to what first. Because when there's other groups there, that's when you then go to the second group. So the second group that would be bound here is a hydrogen, whereas in the carboxylic group, it would be an oxygen. So that's how we know that this one takes, 2 and 3. So that's how we know that that one takes precedence over the methyl. So don't get confused and think, oh, there's 2 oxygen here or something like that. That must be priority over the hydroxide. It's what the first thing is bound to. Another common mistake I see is adding them all up, so getting the collective molecular weight. Again, it's only the first atom that it's bound to. And if the first atom is tied, that's when you would go to the second atom, as in the case of the methyl and the carboxylic acid. Okay, so that's step 1, prioritize. Now we need to get the hydrogen facing away from us. So which one of these wedges is away from us? Well, it's the dashed wedge. So this is just something that you'll need to remember. But so this is where our rotation comes in. So again, we need to get the hydrogen over here. So we could do anything really, but just to make it easy, I might just hold that methyl group. So I'm holding the methyl group at the top. So that means it doesn't move and everything just rotates around it. So that will move the hydrogen out here, and it means the hydroxide will go over here, and the carboxylic acid will come to the bottom, and OH. Now we still bring across those priorities. So the priorities haven't changed. We've just moved, we've just moved the groups. We've just rotated the groups around that carbon, but they still have the same priority. So that's step 2 done. So now that we've got the hydrogen pointing away from us, all we need to do is then kind of I like to just think of it as connecting the dots from 1 to 2 to 3. So we ignore number 4, which is the hydrogen. I'll just make a quick note. I've never seen it happen, but if there isn't hydrogen, it will just be the 4th priority group. But I've only ever seen these questions with hydrogen, so it's always hydrogen. But just thought I'd mention that. So it's connect the dots between everything but the fourth priority group. So what I mean by that is we go 1 to 2 and then 2 to 3, okay? And what we need to do is see which way around I like to think of it as which way around, if you were going around a clock, which way do your hands go? So if you kind of follow my hand here, it's going around to my left, okay? That might be opposite for you. But if you look at that molecule, it's going around to the left. If the arrows were going this way, it would be going around to the right. All right, so either left or right. And I find that R is the easiest to remember because the R configuration is if they're going to the right. If they're going to the left, it's S. So if you can remember that R for right and then just reverse engineer it. So here we have these ones going to the left, so that's not R, not right, so it's not R, so it's S. So this one here is an S configuration. Whereas if the numbers were like this, so I'll do them in purple, so let's say 1, 2, 3, those arrows are going to the right, which means it's an R configuration. So ultimately, when you do get these, you're going to get the molecule and it's going to say the R configuration is found in which molecules or something like that. So if you just need to kind of follow this process, so you prioritize the groups and then you use your rotation. So you see why that's such an important skill. You rotate them so that the hydrogen is facing away from you, and then you just kind of connect the dots. And it's very, very important that you don't forget that hydrogen step, because sometimes people forget it and they still get the right answer, but you won't get the right answer every single time. Just by chance, sometimes you can somehow get the right answer, but I think don't rely on that. Just really make sure that you add in that hydrogen step. So I hope you enjoyed the video. As I say, just knowing these three things really well has got me really far through the GAMSAT in terms of stereochemistry. And they're quite simple. Once you get your head around, I find the rotation is the hardest one, but once you get your head around that, really it's quite easy and straightforward. So I think that it's definitely worth putting your time into. I see a lot of stereochemistry questions, and I also see a lot of people who don't really understand it very well. So if you put the time in, I guarantee you'll see the reward for effort.